Hello. Today we will present our project, our 10 project titled 28 gigahertz channel sounding at Hunt Library, North Carolina State University. The presenters are Martin Izuma and Vagish Anandamba. The objective of this project is to investigate the indoor propagation characteristics of 28 gigahertz millimeter wave signals inside an ultra-modern Hunt library. We are interested in extracting the persistent multipath component in each scenario and compute its angle of arrival and angle of departure and multipath component power, that is power of the multipath component. We're also interested in computing the delay spread, the root mean square value of the delay spread, and the plotting the power delay profile. We hope to draw inferences from our measurement, inferences like the blockage, grouping, existence of persistent multipath, and compute the path loss coefficient. Why are we interested in millimeter wave channel sounding in the first place? This is because three technologies have been identified, or three broad technologies have been identified as the enabling technologies to realize 5G. The first is network densification, that is designing more small cells to bring the network to get the user closer to the base station. The second is spectral efficiency, which exploits massive MIMO techniques and beamforming. The third is to transmit at higher frequency band, and millimeter wave frequency band has been identified as a good potential. This is because the sub 6 gigahertz bandwidth has been highly saturated. So there is need for us to understand how to transmit at these millimeter wave frequencies. However, there are challenges to transmitting in the millimeter wave frequencies, and this is due to attenuation and blockage in indoor environment, blockage by furnitures and partition walls and floors, and general attenuations and absorption by gases and other things. Therefore, it is important to analyze the propagation properties of millimeter wave transmission and compute the delay spread and get an idea of the propagation and compute the propagation exponent. This is the objective of this project. As mentioned earlier, our experiment was carried out at Hunt Library. Hunt Library is located in the Centennial campus at North Carolina State University. This is an ultra-modern library with a lot of good and modern furnitures like made of glass, wood, and plastics which constitute blockage to millimeter wave transmission. In our experiment, the transmitter is placed in the second floor and the receiver is moved to different positions in and out of the library. Here we have an indoor view of the Hunt Library. As we can see, the blockages are mainly due to furniture and accessories in the library. What is a channel sounder? Basically, a channel sounder consists of a transmitter and a receiver used for investigating or measuring the channel impulse response in different scenarios. Basically, for our experiment, our channel sounder is built around the National Instrument PSI modules, which are measurement modules for instrumentation, instrumentation and measurement. So besides the PSI, we also have a rubidium clock for synchronization, and we have a gimbal for automatically moving the antennas. We also have 28 gigahertz horn antennas for transmitter, which actually transmit signals from the radio front end. The radio front end operates at 28 gigahertz. The software that controls the whole system is the LabVIEW software for instrumentation and control. Here we describe the different measurement scenarios. The first two measurement scenarios are line of sight alignment between the transmitter and the receiver. The third and the fourth are scenarios where we have partial line of sight. The fifth and the sixth are non-line of sight scenarios. The seventh scenario is when the receiver is at the fourth floor and the transmitter is on the second floor. And the eighth scenario, which is the last, is when we have the receiver outside the library. And so scenario 1 looks like this. You have the transmitter and you have the receiver. Both of them are 5 meters away from each other, and we have blockage like walls and furnitures around. This slide shows the result for the first scenario. Here, as you can see, we have 9 scatter plots, and on 9 scatter plots where we plotted the powers of the receive multipart component for different combination of transmit antennas and receive antenna, both azimuth and elevation angle. On the horizontal, on the first row, we have the transmit antenna. The elevation of the transmit antenna fixed at 20, and elevation of receive antennas vary. On the second row, we have elevation of the transmit antenna fixed at 0 and different elevation for the receive antenna. On the third row, we have elevation angle of the transmit antenna fixed at -20 and different angle for the elevation angle of the receive antenna. We discovered that in all these scenarios, this particular case where the elevation of the transmit and receive is 0, we receive high number of multipart components, and with majority of them with the high power multipart component lying in a small angle range between 0 to -100 azimuth angle, both for the transmit and the receiver, on the both on the negative and on the positive side. And this is due to reflectors that are close to the transmitter, which are and chairs that are very close to the transmitter, and the glass windows, and this actually causes high multipart power for these angles. So also we discovered that in general we have a good number of multipart for the different plots, except in these cases where we have very sparse number of multipart component, which is due to reflections from walls that are far away. So we can see that for this plot, this second plot here shows here we investigate the existence of persistent multipart component for this first scenario, that is the 5 meter line of sight scenarios. So here you can see there are persistent multipart component occurring at this angle, and they also occur here, and they also occur here. So we notice the same trend here, we notice the same trend here, we notice the same trend here, and a few of them are grouped here. This is grouping, which is important, though we have sparse distribution of multiparts, very few and highly sparse, because the receive antenna is looking at the floor and on the floor, and the transmit antenna is also looking on the floor. But both of that, so according to the two-ray model, we expect reflection from the receive from the transmission on the floor to the transmitter. However, it depends on the angle of incidence. In this case, at 20 degree, the transmitted wave, millimeter wave or signals are reflected away from the receiver. So that explains this scenario. But it is important to notice this grouping. And in most cases, like in this case, we discovered that although there are a lot of multipart, there are fewer multipart here, and this is due to blockage. Though we still get some, but they are low in number. This is due to blockage by furnitures in the environment. So here we explain how to derive how to plot the power and delay profile. Here we have to calculate the mean delay as given by this formula, and we calculated the second moment, which is used to compute the root mean square for the delay. So to actually plot the delay profile, we plot the multipart power on the vertical and the delay in nanoseconds on the horizontal. And from this we can see that for different elevation angle for both the transmit and the receive, we have different values for the ROMS delay. Why is this important? We need to find the multipart with the lowest delay. This multipart with the lowest delay can give us an idea of the coherence bandwidth of this of the channel. So this is very important. In this case, the last row corresponds to the orientation with the lowest ROMS value, the lowest delay. In this slide, we analyze one of the scenarios in one of the scatter plots in the first scenarios, which we are still dealing with, where we have groupings of 3 multi-part components. And this is a case where we have the transmitter elevation angle of -20 and the receiver elevation angle at -20. That is, both the transmitters and receiver are both looking at the floor, on the floor, at 5 meters apart. So we have a groupings of 3 multi-part components, and we see there is a sparsity in the whole in the multi-part component. This groupings is due to blockage in the environment, and why this sparsity is due to can be predicted from the two-ray model, since both of the transmitters and receiver are looking on the floor. So this is not a good deployment scenario, but observation of this grouping is very important. And this is the second scenario, where you have the transmitter and the receiver at 10 meters apart in line of sight arrangement. This is like the similar observation to what we got when they are 5 meters apart. So like in the case where you have, this case is also similar to what we saw before. At low angle, at a reduced angle of transmitter and receiver in the negative direction, reduced azimuth angles, we discover there are more multi-part components due to reflection by blockage, which are, or scatterers, which are very close to the transmitters and the receiver. These have higher power. While in other cases we have, in these cases we have sparsity due to the reflectors. The transmitters and receivers are looking away from each other, and the closest reflector are walls that are far away from each other. This is similar to what we observe when the transmitters and receiver are 5 meters away. Also, like in this scenario where we have 10 meters, this is the second scenario, we have the transmitter in this point and the receiver 2 pillars away from each other, 10 meters away, and we investigated the persistent multipart as we did in the last scenario. We discovered that there are persistent multipart in this angle here. We can find them here. Also, we have similar persistent multipart here. We have similar persistent multipart here, and we have similar persistent multipart here. But in this third column, like in the last scenario, we don't really find persistent multiparts. And also, like the last scenario where we observe very few multipart at the middle, these are due to blockage. This blockage by the seats and the cushion, as we observe in the last scenario. So also we investigated the delay spread in this scenario at 10 meters, and we discovered that we received the lowest the delay spread when the transmitter and the receiver at elevation angle of -20 degree to each other. That means they are looking on the floor. So we observe this delay spread, and this is the power delay profile. So also now in this other scenario, we have the transmitter and the receiver placed in around the bookshelf. It's actually covered by a bookshelf. So in this case, we have and due to blockage, we receive no multi-part in this scenario. This is because the receiver is looking on the ground, and so is blocked by the bookshelf, which we will show later. Like in this scenario where you have the transmitter and receiver at 0 degree, we receive good multi-part component with good power at an angle less than 100 degree for the azimuth and receiver angle. Similar observation as the last two scenarios. But the interesting thing about this is having this blockage with high sparsity. So we also investigated the persistent multipart in this case. Like you can see in the scenario where the receiver is looking on the floor, we see the sparse scenario. We just have one multipart component. Here's the receiver, and transmitter is somewhere behind. So receiver is looking down on the deck. So people who are seated here may have problem with coverage. Also here, we notice that the persistent multipart we saw in the first case is also present in the scenario. and here we have a little of it, and this shows that, and also in this case we still have the persistent multipaths. And we have another scenario, the fourth scenario, where you have the transmitter still in the second floor and the receiver is 53 meters away in partial line of sight alignment. So in this case, we have no multipath here where the receiver is looking below and it is totally blocked from the transmitter. So we observe the same here, very sparse. And still in this scenario where you have the receiver and transmitter at 10 degree, we get good energy at minus 100, below minus 100 azimuth and below minus 100 degree for the transmitter and the receiver. This seems to be recurrent for all scenarios so far. But in this case, at long distance and in partial line of sight, we see a lot of sparsity. Here we also investigated if we get this persistent multipath component. We observe they are almost non-existent in the first column, where the transmit receive angle is 0 degree. Unlike what we saw in the last three cases, and the persistent multipath component, we can't find them in this case. We can't find them here, and in this case we receive very few multipaths. So these are sparse, so like we observe in the other scenario in the last cases. So here we investigated the non-line of sight scenario where we have the receiver hidden in a corridor away from the transmitter. In this case, we observe some multipath component is becoming persistent for all scenarios, and but we also observe very few multipath components when the receiver is looking down, as we observe in similar scenarios. But it's interesting to know that even in a non-line of sight environment, we could still get receive multipath components at 12 meters away. So we investigated, and this is the corridor, and we investigated if there are persistent multipath as we did in time past. And in this non-line of sight scenarios, we discovered that there are persistent multipath in this case here in this transmit and receive transmit azimuth at 0 degree and receive azimuth at about 100. So we discover persistent multipath here, and we can see the sparsity generally. So the receiver is hidden somewhere here. You can see the cable, and the transmitter is hidden here. This is a corridor. And in this case, we also try to, this is non-line of sight scenario, and we put the receiver hidden inside a glass room which is hidden. And in this scenario, like what we saw before, we still could see multipaths, good multipath component with some good power when the transmitter and receiver are 0 degree elevation angle. But we receive more sparsity in the scenario, non-line of sight scenario, with the receiver inside one of the rooms, more sparse. But sometimes we observe there are power multipath received here and multipath received in these scenarios, and this occurs when the receivers is looking towards the glass door. So when it's looking away from it, we get less multipath. But also the multipath powers received are also much lower.
22.
Yeah, I went to this one.
Laser pointer.
In this case, we investigate if there are more persistent multipath components when the receiver is inside the room, as you can see. Here we realize there is a special case where there is virtually no multipath here. Here the receiver is pointing at the wall away from the glass window. And as you know, this is a non-line of sight scenario, so we discover there are very sparse multipath components. But in this case, we discover a lot of multipath. In this case, we have the receiver on the 4th floor and the transmitter in the 2nd floor. We discover there are a lot of blockages when except in scenarios where the transmitter is looking at at 20 degree, that is looking up, so it can actually see the receiver. But in this case where the receiver is looking down and the transmitter is looking up, we discovered there are virtually no multi-path component. So in general, this is quite sparse, except in this scenario where the receiver and the transmitter are at 0 degree. So in this scenario, we try to investigate if there are persistent multi-path component. That is when the receiver is on the 4th floor. Like here, very sparse, we see there is only one multi-path component. In these two cases, there is a persistent multi-path component. In this case, we have persistent multi-path component, but this is not very frequent. So as you can see, in this case, we have the receiver outside the library and the transmitter inside the library. We wanted to investigate the attenuation effect of the glass, and we increased the power of the transmitter. Though we increased the power of the transmitters, we discovered that the signal is very sparse because of the blockage, which is the glass wall in between the transmitter and the receiver. So this is a very special case and worth noting. Here we have the receiver outside, and we discovered, as we can see, there is very sparse, the multipath and scatter plot is very sparse, but there is an interesting scenario where we have a persistent multipath component. Generally, we see the effect of blockage, but here we seem to have some grouping here which can be further investigated.
After having investigated for various scenarios, the delay spread, angle of arrival, angle of departure, and how various multipaths group together for a particular transmitter and receiver azimuth angles, we now turn our attention to calculating the path loss for the 3 broad scenarios that we have considered. The 3 broad scenarios that we have considered in this project are the line of sight communication, the non-line of sight communication, both within the indoor premises of the library, and the line of sight communication when the transmitter is inside the library and the receiver is outside the library. The 2 graphs shown here are used to measure the path loss for the line of sight communication inside the library. The graph on the left shows the path loss in dB versus the transmitter and receiver distance that has been extrapolated to measure about 120 meters, and we can see that the path loss saturates to about 98 to 99 dB, while the graph on the left shows the distribution for the shadowing variable plotted in dB scale, and hence turns out to be a Gaussian distribution. Had it been in linear scale, it would have been a log normal distribution. These graphs show the path loss measurement for the non-line of sight communication inside the library premises. As before, the graph on the left shows the path loss versus the transmitter receiver distance that we have plotted to about 25 meters, which in our library environment is the maximum non-line of sight distance, and we can see that the path loss saturates again to about 96 to 97 dB. The graph on the right now shows the shadowing variable that again follows approximately Gaussian distribution, and hence if plotted again in the linear scale would be a log normal distribution. The path loss measurements for the scenario wherein which the transmitter is inside the library and the receiver is outside the library is shown here. The graph on the left again shows the path loss to saturate to about 112 dB, which is way higher than the 2 previous cases, and this is intuitive since a lot of absorption of the signal power occurs due to the huge glass wall that is present that divides the premises of the library. The graph on the right shows the Gaussian distribution for the shadowing variable as before. So to conclude, the propagation characteristics of a 28 GHz millimeter wave communication system for an indoor environment was investigated in this project. The major finding was that there exists many dominant multipath components for a particular scenario, and it is up to the network designer's ingenuity to utilize these multipath components in designing an efficient network. Finally, we calculated the path loss exponents that could be present for the 3 broad scenarios, and the values are as tabulated in the slide. Hence, the take-home message is that while designing a network using millimeter wave communication systems, the orientation of transmitter and receiver are extremely important, and we have to very carefully use the dominant multipath components to our advantage. Thank you.